Let's talk about music. That's right, in my everlasting wait for the release of the Zero calculator, I've finally decided to give up calculators for good and move on to a new hobby. Just kidding, I have way too many unfinished projects to ever retire from calculators, so don't worry, I'm here to stay. However, that doesn't stop me from thinking of new ideas for even more projects in the meantime. About a year ago, I had a bit of an itch to make some music. Of course, I knew I wouldn't make anything particularly good, but that didn't stop me from looking up some stuff about digital music production and quickly becoming overwhelmed by software and hardware I could never dream of being able to afford. That's what brought me to MIDI keyboards. A USB MIDI keyboard is a bit like a piano or synthesizer, but rather than playing any notes itself, it outputs note events over USB to something else, in my case, a computer program, which translates them into sound. I won't go too far into the specifics now, but trust me, by the end of the video, neither of us will ever want to hear the words USB or MIDI again. Now, my first plan was to simply purchase a used keyboard from an online thrift store auction, but in my never-ending attempt to save money, I thought that it would be much easier to just make a program for a calculator I already owned. A calculator can connect to a computer via USB, which means that we should be able to write a program which would allow it to be recognized and used as a MIDI keyboard. I decided on the TI-84 Plus CE, since I can use the C programming language with some USB libraries that should make programming it a piece of cake. However, it was then that I realized the crucial flaw in my plan. I have absolutely no idea how USB works, let alone MIDI over USB. It shouldn't be too hard to figure out though, or at least that's what I thought. My initial goals for the program are pretty straightforward. I want to make the calculator compliant with the USB MIDI standard, meaning that no additional software or drivers are necessary for a device to recognize it as a MIDI keyboard. The first step we need to do is transmit what's called a descriptor, which tells the computer the specifics of the device it's talking to. Once the computer receives the appropriate descriptors, it is able to receive event packets, which are essentially small bundles of data that get interpreted by the software running on the computer. The calculator program should be able to detect key presses and then send appropriate event packets when the keys are pressed. At this point, it's up to the computer to output them as sound, use the notes in a loop, or do whatever else it wants to do with the MIDI input. I'd like to give a huge thank you to PowerByte7, who provided me with a device descriptor of their USB MIDI keyboard. I planned on mimicking this until I got something working, and it was a good start for the project. PowerByte was super helpful throughout the whole project and put up with a lot of dumb questions from me, so they deserve a huge shout out. After borrowing some code from one of their projects, I had a program which I assumed should get the calculator to be discovered as a USB MIDI keyboard. This assumption, along with many future assumptions I will make in this video, was in fact not the case. At this point, I still hadn't figured out how to debug the descriptor packets I was sending to the computer, but PowerByte was able to test it, and we figured out that for some reason one of the parts of the configuration descriptor was being truncated, meaning only the first part of it was being sent. To fix this, I turned to my tried and true solution for all software issues: ask somebody else for help. This was not super effective though, and it was at this point I lost motivation and did other stuff for 3/4 of a year before forgetting how painful the project was and deciding to give it another shot. It's probably also worth noting that I cut a significant amount of trial and error that went into this project because I thought it was too boring, but if at any point you get the idea that I am somewhat competent throughout this video, that is probably not the case. This time around, I also talked to Command Block Guy, one of the developers of the USB library I've been using. He also deserves a huge shout out for putting up with my shenanigans as I struggled to figure out what was going wrong with the descriptor. He suggested that the issue could actually be coming from the library itself, and I would need to send the descriptor manually instead of using its automatic function. This was not the answer I was hoping for, but sending the descriptor manually turned out not to be too hard, at least in theory. All that we need to do is intercept the request for the configuration descriptor from the computer and then send it ourselves before it gets automatically handled by the library. Because I didn't really know how to do this, I threw in some if statements to check for certain events which would display a color on the screen if the program reached them. This way we can figure out exactly what if statements we need to check for the request. I spent a few days messing around with colored screens and getting no result, until I realized not even the partial configuration descriptor was being sent to the computer anymore. I tried switching the cable, reinstalling the USB library, and even using a different calculator entirely, until eventually remembering that I had changed what's called the max packet size at some point. Changing it back fixed it, and within an hour or two I was able to pinpoint the exact event I needed, along with the USB event data I needed to check for in order to send the descriptor over myself. Yet again, it took me some trial and error to figure out how to actually transfer the descriptor, but thankfully the library has a lot of example code we can look at, which made the transfer not too bad. With the descriptor going through now, we can check again to see whether the device is recognized by the computer. The device appears fine in LMMS, the digital audio workstation I'm using on Linux, but when I tried it on Windows, Device Manager said it couldn't start. I decided not to worry about that too much for the time being, and moved on to sending the first USB MIDI event. There are a number of different types of USB MIDI events, but to keep things simple, I think it makes sense for us to start by trying to send a note on event. According to version 1 of the USB MIDI class definition, events are made up of 4 bytes. The initial byte is reserved for the cable number and code index number, and the remaining 3 bytes differ depending on the event. The event itself is determined by the code index number, and since we're using a note on event, that number is 9. To complete the byte, we'll also need to provide a virtual cable number in the upper 4 bits, but for this I'm just going to put 0. The next byte, for most events, is similar to the initial byte, but this time the event type is stored in the upper 4 bits, and the lower 4 bits are used to specify the channel. Again, for this test, I'm just going to use channel 0 to keep things simple. The final 2 bytes are much more specific to the note on event. The first of these is a velocity value, which determines how hard the key was pressed. Since there isn't a way to detect this on the calculator, I'm just going to hard code a velocity, and for now I chose 7F in hex or 127 in decimal because that's what PowerByte's keyboard used. The final byte is a number associated with the note being pressed. I found a site online which documented the numbers associated with each note, and for our first test I think it makes sense to use A4, as it is a commonly used pitch for tuning musical instruments. With everything set up, I decided to give it a test, which definitely worked on the first time. After a decent amount of bug fixing, I got it to send the note event correctly on Linux. However, when I gave the program a second try on Windows, I ended up actually causing not the calculator, but my computer to crash. After significantly more crashes, research, and somehow breaking my Windows audio drivers multiple times, I found this website which I used to create a new descriptor. It was super helpful and definitely what I should have done from the very beginning. I had to make some tweaks since the site generates a descriptor for MIDI 2 but the program uses MIDI 1, but after that, the new descriptor fixed the crashing issue. I was able to test the program with macOS, Chrome OS, and Android, and it works on all of them. I don't have any iOS devices to test on, but I'd assume it works on there too, given the success on all the others. Getting the device recognized as a MIDI keyboard was a major step. Now that we can send MIDI events as well, it's time to move on to something a bit more fun, designing the keyboard layout for the program. Given that keyboards are typically a more horizontal shape, I think it makes sense to rotate the calculator when using it as a MIDI keyboard. I reserved this section of keys for note input, and I'd like to make this section of keys a drum pad, since I've seen quite a few USB MIDI keyboards which can do both drums and regular notes at the same time. For the actual layout of the notes, I decided on a bit of an unconventional design. On a regular keyboard, you'll notice that there's a row of white keys and black keys offset at specific intervals. However, because the keys on the calculator are more or less aligned with each other, having occasionally offset keys would be a bit weird and result in a few unused keys, which seems like a waste. When working with notes for a keyboard like this, we can describe the notes as either being a half step or whole step apart. A half step interval sounds like this, and a whole step interval, or 2 half steps, sounds like this. For my layout, I've arranged the notes on each horizontally adjacent key to be 1 whole step apart, and the notes on each vertically adjacent key to be 1 half step apart. This makes transitioning from an instrument like a piano a little difficult, but I found it actually to be kind of convenient to learn since all the notes are at a standard offset. Along with the keyboard and drum pad, I want to add octave shift keys, which will let you adjust the keyboard up or down by 1 octave. This lets you play a wider range of notes, since you can adjust the keyboard to begin at a higher or lower pitch, like this. I've also reserved these 2 keys for pitch bend adjustment, which lets you slide and adjust the pitch of the currently active notes very slightly. Finally, the bottom rows of keys will be used as MIDI controls, which can be mapped to values in the computer software to adjust certain values. Each control consists of 2 keys, the left key which lowers the value, and the right key which increases it. I also decided to add a few other features to the key map later, but we won't worry about those for now. I started implementing the pitch bend feature first, since it seemed to be the most straightforward. We only need to handle two keys, one which will increase the pitch bend value and one which will decrease it. When no keys are held, the pitch bend should automatically slide back into its original state and correct itself. I found a useful site which helped me better understand exactly how I need to format the pitch bend event. The pitch bend value is a 14-bit number, split into the lower 7 bits of 2 event data bytes. This means that the minimum pitch bend value is 0, and the maximum is 16,383. MIDI expects the most significant bit of each data byte to be reset, or 0, which is why the pitch bend value can only take advantage of the lower 7 bits. For my first test, I only modified the most significant 7 bits of the pitch bend value, and left the least significant 7 bits as 0. This involved a bit less math and was lazier to implement, but it also has the downside of allowing less precision since we're only working in intervals of 128. My first test was reasonably successful, at least compared to my history with this project. I mixed up the keys responsible for the pitch bend change, and it also seemed to be a bit less gradual than I would have liked due to the lack of precision. Fixing the mapped keys was simple, and to fix the speed of the change, all we should need to do is make use of the lower 7 bits of the pitch bend value. Since working with a single 14-bit number split into two 8-bit numbers that are actually 7-bit numbers is a little annoying in C, I copied some code to split the value into the 2 MIDI event bytes and saved myself the trouble of actually thinking about bit math. After a bit of tweaking to get a speed I was happy with, I decided to move on to the next thing, the keyboard and the drum pad. In order to play multiple notes at once, we need to be able to handle multiple key presses at once. To do this, we can take a snapshot of the keypad data, and then compare it with the current keypad data to check if any values have changed. If a value in the keypad map has changed, that means that the key has either gone from unpressed to pressed, or pressed to unpressed, and we can trigger a note on or off event accordingly. To determine which note to play, I created a 2D array where each entry contains the value associated with the key at the same location in the keypad data. Since the keypad data is stored in bits, we can imagine the note data as having 6 rows of 8 columns, where each row represents 1 byte in the keypad data and each column represents 1 bit in each byte. For keys without any note associated, I put a 0 in the note map. If you remember from earlier, MIDI event data bytes require the most significant bit to be reset, which means all the MIDI note values are 7-bit numbers. We can take advantage of this by using the most significant bit in our note map to denote whether or not the key is a part of the keyboard or the drum pad, and then mask that bit out later when we transfer it so that I don't end up crashing my computer again. When compiling my first prototype of the keyboard code, I continued to run into warnings with my keypad data backup, saying that I was trying to store a 16-bit value to an 8-bit number. I messed around with the code until I got it to stop complaining, which totally shouldn't cause any future issues. This version performed quite poorly, and for some reason keys could not be released. After testing the program with a debugger on my computer, I was able to look at the memory view and discovered that I had made some assumptions about the keypad data when I was backing it up that were causing a lot of problems. It turns out that, as the warning suggested, the keypad data array is made up of 16-bit values, where only 1 byte of each seems to actually be modified. With this new knowledge in hand, I was able to quickly rewrite my keypad backup and get something that actually worked. During testing, I noticed that certain keys were registered as being pressed without my fingers ever actually pressing them. It took me a while to find the cause of the error, since I wasn't able to reproduce it when testing in CMU, the TI-84 Plus CE emulator and debugger I've been using. However, with the help of the CE programming Discord server, I was eventually able to determine that the calculator's keypad hardware is prone to an issue called ghosting, where combinations of 3 keys being pressed can lead to the keypad falsely detecting a 4th key being pressed as well. This can be corrected at a hardware level, but there isn't really any solution in software, as there's no way to tell if a key is actually being pressed, at least as far as I'm aware of. Thankfully, pressing combinations of keys which cause the issue to be noticeable is pretty rare. The ghosting issue also inspired me to add one more feature, a sustain button. Similar to the sustain pedal on a piano or keyboard, holding this button causes all currently played notes to continue playing even if their keys are released, until the sustain button is released. Since the VARS key is still free to use from our initial keypad design, we'll use that one. The logic behind the sustain button wasn't too difficult to implement, and here's a clip of me testing it out. All we need to do to sustain notes is delay the note off event until after the sustain button is released, so I just put an if statement in that skips the note off and key release portion of the code when the VARS key is being held down. With note input out of the way, I moved on to the MIDI control section of the keypad layout. I want to be able to map this row of keys to modify certain values, such as volume or modulation, in my software. Each pair of two keys represents one mappable control, where the left key decreases the value and the right key increases it. I made a 4-byte array to hold the control values for each set of keys, and all we need to do to register them as MIDI controls is to assign each pair a control ID, and then send the ID and value in a MIDI event whenever the value is modified. I was able to find a list of MIDI control IDs, and I ended up choosing the first 4 since that seemed to make the most sense. This brings us to the last feature of the keypad, the octave shift. This was by far the easiest feature to implement, since it isn't actually even a MIDI event at all, but rather a value which we add to each note when sending the note on or off event. For example, if the user presses the key mapped to the note A4 and the octave shift is set to -1 octave, the MIDI event adds the octave shift value to the note and sends A3. If the octave shift is set to +1 octave, it would send A5 instead. Now, as I've been implementing all these features, I've actually been wishing for some additional settings to be available. For example, it would be nice to be able to modify the sensitivity of the pitch bend control, and since the note velocity isn't determined by the keypad, it would be nice to be able to change that in the program as well. At this point, while the keypad is all used up, the screen of the calculator is still available, so we can display these additional values there and create a sort of settings menu. Before I actually begin coding a display, I like to make a mock-up so I have an idea of where to put things. I stole the color scheme from the Teenage Engineering OP1 since it seemed like a nice interface, and after messing around with different layouts for a while, I came up with this. Since the keyboard is horizontal, I think it makes sense to design the layout of the screen to work with the calculator rotated as well. At the top of the display are 3 dials, which allow you to set the root, or bottom note, of the keypad, adjust the pitch bend sensitivity, and set the note velocity. Below this is an option to switch between a monophonic, or one note at a time mode, and a polyphonic mode, which lets you play as many notes at a time as you want. There's also an option to change the MIDI channel being used, and to switch between dark and light mode, because that's always important. Below the settings, I've put a few different things to indicate the current status of the program. These are pretty self-explanatory for the most part and just reflect the current values. The octave shows the current octave, sustain lights up if sustain is active, and the pitch bend bar shows the current pitch bend value. With the mockup done, the next thing I did was collect all the colors into a palette. The TID4+CE graphics library I'm using sets the display to an 8-bit per pixel mode, where each pixel is represented by a single byte or 8-bit value. To determine what color to display, each value corresponds to an RGB 1555 color in a palette, which can be set and swapped by the library at any time. Now, it is possible to generate a palette automatically from an image, but I decided to do it manually since I want to make sure the color indexes match up with the light mode and dark mode palette. This way, I can swap out the palettes when changing themes and don't have to do anything else. This wouldn't normally be too difficult, but since the dials are anti-aliased to appear more smooth, I need to incorporate a significantly larger number of colors into the palette. Once I finished making the palette, I quickly threw together some code to get an idea of how it would look on the calculator. My results were interesting, and I quickly noticed a few problems. The most obvious thing that's clearly wrong is I forgot to actually set the palette, which leads to all the colors being quite odd. However, I also realized that I completely overlooked the rotated display, which poses a number of problems. Since the display is rotated, using the text routines provided by the graphics library is out of the question, as all the text needs to be displayed at a 90-degree angle. Without rotating the text, it's difficult to read and looks quite odd. I decided on making my own text display routine, which I wrote in Easy80 assembly to make it as optimized as possible. I'm not very good at Easy80 assembly, so it's probably not as optimized as possible. It makes use of pre-rotated font data and handles a minimal number of cases specific to this program, which not only made it easier to write, but also helps with the speed and size of the routine. After a few tests of the custom print function, I was able to confirm everything worked as it should. With the text done, I moved on to the other elements of the display. Everything else was pretty straightforward to draw, though I did run into some slowdown issues at first when redrawing the pitch bend bar. The last step is to actually make the settings modifiable. Is that even a word? I don't know. But most of the settings were already in my code as a hard-coded value, so it didn't take too long. Designing a light mode took some time to get the palette lined up correctly, and the monophonic voice took a bit of work, but overall it went much smoother than previous parts of this project. In order to modify a setting, you can press the zoom key to disable the MIDI input and enter in editing mode. From there, it's as simple as selecting the setting you wish to modify, pressing second, and then using the arrow keys to adjust the value. Obviously, the best part of the project is actually using it, which is probably why you came to this video in the first place. So here's a quick demo. Feel free to check out the project for yourself on GitHub and download it if you're interested in giving it a try on your own calculator. You can find more detailed instructions for setting it up yourself there, and the source code is available as well if you're interested in taking a look or contributing something. I don't really recommend it though, because it's probably pretty bad. This is the first video I've done covering a project like this, so please feel free to leave any feedback in the comments section. As always, this has been Tiny Hacker, and I'll see you in the next video.